So in this video, we will use the series sum to generate the Taylor series expansion of hyperbolic cosine, and we'll use LINEST in the polynomial regression of the expansion and its function itself. So we have a hyperbolic cosine function. We generate the dataset from for values of -3 of x to +3. So our formula cosine hyperbolic of the x values. We regress it with the best fit using chart, scatter chart, and the trend line should be the best fit. So we will use polynomial to the highest degree. So we will show the equation of the polynomial. So we'll improve that to 6 degree, where you have perfect 1 for r squared. And we'll expand the polynomial. We'll expand the function, Taylor series expansion, because cosine, hyperbolic cosine equals the summation of x to the power 2n over 2n factorial. The coefficient 2n factorial contains n that starts from 0 to infinity. So our values of n will be from 0 to infinity. In this case, we can only reach up to the maximum 6. We'll just do for 6. So the coefficients will be our formula, factorial 2 times n. And it is a fraction, so 1 over factorial. So now we have the coefficients. We can now calculate or generate the expansion, which is our formula, series sum of the x values raised to the power. So the first degree will be x to the 2n, so that's 0. 2 times 0 equals 0. And the next will be 2n. 2 times 1 is 2. So 2, then 4 and 6. So that's an increment of 2. And the coefficient will be this range. So we have this value, which is a very good approximation of the hyperbolic cosine, the expansion. We will add this to the chart and see if that fits. So edit chart, add a series, and show this trend line. You'll notice the red ones are in the trend line, meaning they are almost the same. The expansion is a good approximation of hyperbolic cosine function. We will also generate the trend line using the same format, that is polynomial to the 6 degree. The red line, and we show the equation as well. See if the regression coefficients are the same. So we show the equation. And yes, it confirms. B0 is 1, B1 is 0, B2 is 0.501, B3 is 0, B4 is 0.0403, and B5 is 0, B6 is 1.78 times 10 to the minus 3. So they have the same coefficients. We will calculate these coefficients using LINEST. So to do that, we will enter the LINEST. So we start with we'll generate the power to the 6th, because it is to the 6th degree. So this will be our formula. Oh no, this is transpose of this value up to 6. And we generate the 1 comma x matrix. So we start with the one column, which is our formula of the x matrix. raised to the power 0. So that's the one column. And we lock the reference. We lock the reference. And this will be the x column, which matches to our x values. Then this will be the x squared column, the x cubed column, and the x to the fourth column, x to the fifth column, and x to the sixth column. Now that we have the 1 comma x matrix completed, we started generating the LINEST for the hyperbolic cosine function, which is LINEST of data y. This will be our data y and data x, starting with the x column. And for the expansion, it will be LINEST data y and the data x. You will notice B0, B0 all the same, B1, they're both the same. B2, 0.50104, they're the same also. B3, all 0. B4, 0.4025, they're the same. B5, 0. And B6, 0.001779, they're also the same. So this completes the use of series sum in generating the Taylor series expansion and LINEST in the polynomial regression of hyperbolic cosine.